So the thing is that because in quantum mechanics, only relative probabilities matter. Okay, so only relative probabilities matter physically. Or relative, I should say, amplitudes. Which of course implies relative probabilities. So that means that if you have a state described by some vector psi, another state described by a vector psi times lambda, where lambda is some generic complex number, not a function, then these are the same state. So these are the same state. So
that means if two vectors are linearly independent, they define the same state.
sorry?
Sorry, if two vectors are linearly dependent, they describe the same state.
Exactly. Yeah. No. If they're linearly, yeah, exactly. Yeah. So I mean, there's a little bit of a issue there. Let's see if I. So suppose that if we have three vectors, psi1, psi2, and psi3, right? And suppose that they're not linearly independent. So that means that there is psi1 plus c plus c1, c2 plus psi2 plus c3 by psi3 is 0, right? So this is what it means to be linearly dependent, where c, say 2 and 3, are not 0. So in that case, psi1 is equal to minus c2 psi2 minus c3 psi3. So while, this vector is describe the same state as this vector times some lambda, I would not say that this vector and say this vector describe the same state. Although they are linearly dependent vectors, they don't necessarily describe the same state. Okay, so it's only when you go to more than two vectors this becomes clear. So while there is some truth in what you're saying, I think a better way of saying that is that the physical Hilbert space is a projective vector space. Okay.
Would it be correct to say that if the vectors are on each other's span, then they are the same state?
So each what?
If the vectors are on each other's span, then they are the same state. Like if one vector falls on the same line as the other vector is on.
No, that's what I'm saying. They're not.
Oh, I see. All right.
Because this guy is obviously in the span of these two, but this is not equal to this or this. Okay. So this vector is a different vector than this or this.
Understood, sir.
Okay. So one way of saying it is that the Hilbert space, the physical Hilbert space, is a projective vector space. Sometimes I was taught that the state of a physical system is described by a ray in the Hilbert space. Ray meaning a direction. All right, good. So you will see that for a vector for the system that we're describing, the spin half, the vector space is actually an S1, which is a sorry, not S1, S2, a two-dimensional sphere, which can be shown as a complex projective space, CP1. Okay, so we can use these freedoms, the freedom to rescale vectors, and the fact that only relative amplitudes matter, to rescale our coefficients in this case so that they square to 1. So this is a three-dimensional space, right? It's S3. But of course, there is we can multiply the state by a phase. This does not preclude us a phase. There's still a phase that we can multiply our wave function with, because a phase will not change this. So if I take psi and multiply it by some phase, this will not change this equation. So using that, what we can do is that we can show that we can choose C up to be cosine of theta by 2, and C down to be e to the power I phi sine of theta by 2. And we can then represent these coefficients as coordinates on a two-dimensional sphere. Okay. So if this is, say, this is theta and this is phi. And the north pole of this two-dimensional sphere, so this is a Hilbert space. This is not physical space, okay? So the north pole is going to be this guy, and the south pole is going to be this guy. And let me give you the range of these coordinates. Theta goes from pi to 0 to pi, and phi goes from 0 to 2 pi. Okay.
So the circle or the 2D sphere you
It's
just
a sphere, yeah.
2D sphere, does that mean it's a circle?
No, it's a sphere. Sorry, I should have drawn three-dimensional.
Oh, okay.
I should give it a
Got
shade. Yeah. Okay.
So wouldn't
So-
it be 3D?
No, it's a two-dimensional surface, right? S2.
Oh, the surface. Oh, okay, got
Yeah,
it.
the surface. So when you include the inside of the sphere, which we will have to eventually, when we go and describe more general states, that's when it's called a block sphere. Although a block sphere is actually a block ball. So the block sphere will come to that. It includes the surface as well as the inside. So the kind of vectors that we are envisioning will be points on the surface. So any arbitrary point, any arbitrary state of this system will be described by some unique point on the surface of the sphere. But in the next lecture, we'll see that we actually need to go inside the sphere to describe more general states. And so that is known as the block sphere, the surface and the inside. Although technically it should really be called the block ball. Okay. So before I go and take the attendance, let me just say a few words about the continuous case. So for the continuous case, when we make an observation, say of the momentum, so observation, we should get one of its eigenvalues. So what are its eigenvalues? Its eigenvalues would be a solution to this equation. So this would be an eigenvalue. So if I take a one-dimensional example, so that my momentum operator is not a vector, and it's given by minus IH bar d by dx, then this equation is just a differential equation, right? And the solution of this equation, let's call it, so it's customary and useful to label eigenfunctions or eigenstates by the eigenvalue. So this will be given by 1 over square root of 2 pi h bar e to the power minus or plus px by h bar, where p is this number. Let me use the same kind of calligraphy. Okay, so this is the momentum wave function, and this is a real number. So the eigenvalue, the allowed eigenvalue of the momentum operator is any real number. So the momentum can be anything from minus infinity to plus infinity. Okay? And this normalization is a convention. So when we come to the continuous case, there will be examples of wave functions which are not normalizable. Okay? And this is one of the examples.